The fact that the 8 puzzle, the search space, usually fits into memory means we can do some interesting analysis on this. So here's the example we've seen earlier. This is the same initial state we've seen before. What we have for this initial state is that we can move in all 4 directions. So we have 4 successors for the state, and they're shown here as the 4 successors of this node. Note that all the arrows here are bidirectional, because in this search problem, as in many others, actions are reversible, which means I can always go back and forth between one state and one of its successors. So there's already a little optimization potential for our search algorithm. We can avoid reversible actions. So looking at the successors, we have 3 possible actions here, but of course one of them would us get back to the initial state. So in fact there's only 2 successors that we would generate here. For this, again, we have 3 possible actions here, 3 possible actions, and there are 3 possible actions, which means for each of those successors we generate 2 more successors, as shown here. So we'll look at one example here where we have moved the empty tile up. And this gives us those 2 successors, and in this case there are 2 actions here and 2 actions there, which means for each of those there's only 1 possible real successor, but again note it's a bidirectional arrow, so we can go back and forth between these states. And so on. I can follow this path and generate more successors. You can see there I've ignored some that I didn't generate or didn't look at in detail, and so on. Here is where I'm simply running out of slide, otherwise I would have gone a little further. And then you would see what I'm effectively doing here is the moves I'm following are simply shifting the empty tile in this circle. And what this means is that eventually this path will lead up here again. We're back at our initial state. So this shows that it's a graph, and it's a graph that contains quite some long loops. And as I've said before, we can actually create the whole search space and then analyze how deep the different solutions are. And this is what this graph shows us. We have here the depth of the different solution nodes. So what we did is we started a generation from the solution node and generated all the different nodes that are available in the search space. And these are the depth at which they are from the solution. And here we have the number of different states that are at that depth. Altogether, there's about 180,000 different states in the search space. And we can see that most of the states are actually at around depth, what is this, 24. So as I've said before, the number of states we generate in both tree and graph search grows exponentially. So what we can expect is that this will initially more or less follow the state space here, that we generate the nodes as they are available. But then for tree search, this will continue to grow exponentially. So this goes up here somewhere and out of the slide. But then we see for the worst case here at depth 31, there's really only 2 different states. And if we wanted to use tree search to search for those states, we would have to generate all those states up here, where in fact there are only 2. So what this would lead us to expect is that tree search is reasonably efficient up to about this depth here, and then becomes incredibly inefficient, and we should use graph search for these worst case scenarios. But then graph search also has some additional costs. We need to maintain that hash table, as we've seen. And comparing states in a hash table, well, depending on the complexity of these states, this can take up quite some time too. So there's a basic trade-off here. Another problem is related to permutations of solutions. By that I mean, if we are given one solution path from the initial state to a goal node, if we can swap some of the states and some of the actions on that path to obtain a different solution path, then this is a permutation of that solution. And this creates problems for A star. Often permutations are allowed if we have independent actions in our domain. So if for all states, if we first apply one action and then another, we get one state, and that is the same state as applying the actions in the reverse order, then we say these 2 actions are independent. We could, in principle, execute those 2 actions in parallel, but since we are only looking at action sequences so far, we have to choose an order. And since the order doesn't matter, we have a permutation in our solution here. The state that is the result of applying these 2 actions, in whichever order we choose them, is the same. Now, why is this a problem for A star? And here is the worst case scenario. This is unrealistic, but it is the worst case. Suppose we are given a search problem where we have an initial state and we've found a path to our goal state, and there are many intermediate nodes here. And our optimal path has a length of n, and the worst case is that all these n actions are independent. It is easy to show that if all the pairs of actions are pairwise independent, then we can basically permute those actions into any order we like, and it doesn't change the outcome of the plan. Now, remember what I said earlier about contours, namely that A star, if the optimal solution length is n in this example, will need to generate all the nodes within a smaller contour. So if the f value is n minus 1, then this is the contour that A star will generate, with the f value being equal to n minus 1. What this means is that it will generate all those permutations that have n minus 1 nodes. So what this means is, in this part, there's n minus 1 factorial different combinations of solutions. And it will explore all these paths before it moves on to the first solution. Of course, then it will find n factorial solutions for this problem, which are a lot of solutions. And you should now understand that there is no way around this, of course. So you can now go and experiment with this by programming all this in your language of choice. Specifically, why don't you try to generate this graph here that tells us how many different states exactly there are at the different depths. So, for example, how many states would you find here at depth 27? That is a question.